Okay, today's the day. Today it gets fun. We're going to do some proving trig identities today. To prove them, it's kind of like what we've been doing, where you have some simplification you're going to do, but we're going to have an equal sign between two sides, and we're going to prove that the two sides are the same. Now, this kind of goes back to geometry proofs. It's not going to look like that, but you have to recognize the whole idea is to prove it without a doubt, not doing it all in your head and just saying, hey, this is true. It's all about the work. So absolutely, positively, have to have beautiful work, have to work vertically. I have to see the steps, just like in the steps of your proofs from geometry. It was step by step by step, same deal. Now, before we get started, here's kind of our guidelines that we can use. Some suggestions to make this work out for us when we work with this. And basically, like I said, you're going to have two problems and you're going to have an equal sign between them and you're going to be simplifying. So one suggestion might be to go ahead and just work with one side of the equation at a time. And you usually start with the more complicated side and see what you can do to simplify it. Another thing, basically what we've been doing, anytime that you can factor, look to do that. If you have fractions, get a common denominator, get them combined. Obviously, we're going to be using all of our identities. To help you decide which identities, look at what's in the final expression. What are you trying to show? If it has sines and cosines, then go that route. If it has tangents, go that route. If you have a lot of different types of functions, we typically will convert everything to sine and cosine because everything can go back to that. But number one, I know it's last, but it's still number one. You always have to try something. You can't leave it blank and do nothing. A lot of the time you try stuff and it's good experience to say, oh, I tried that. That doesn't work. That's not very helpful to do that. So the next time around, you maybe will say, that's kind of a roundabout way. I think I'd be better off to try something different. Always try something. All right, here we go. Let's try one. So number one, you have this mess of stuff, and we're trying to prove or verify that it is equal to sine squared. Now remember, an identity basically is just showing one thing is equal to another. We're showing this is equal to this. Now, let's start with the messy side. Look at all of that stuff. Let's work on simplifying that. And I don't know that I'll have to do anything to the right side. I'm hoping this will all simplify and just end up equaling sine squared. Now, best case scenario, you know your identities. And so there will be no need to be peeking at your notes. But I'd rather you peek at your notes than just sit there and follow along and not really know what I'm doing. We're going to definitely be using all the identities we've learned. Let's start with this number one with this numerator here. I look at that and I immediately see anytime you have a squared with a 1, that typically is going to be a Pythagorean identity. It's a rearranged Pythagorean identity. It would actually end up equaling tangent squared theta. And the other thing that I would want to do is this secant squared theta. I'm going to bring that up and call it cosine squared theta. I managed to get rid of the fraction that way. However, I'm going to go ahead and turn it right back into a fraction with my tangent squared. I'm going to change that to a sine squared theta over cosine squared theta. Remember that you're multiplying, and this I could put over 1. And it would appear that my cosine squared thetas would cancel out. And if they cancel out, I think I'm left with just sine squared theta. And I've done it. I've verified that identity. I've shown that both sides are the equivalent of a sine squared theta equals sine. Both of them are that. Now, looking at this, notice I boxed in my final statement there, and that's good. However, you have to realize that that's not really your answer. Your answer is all of the work, the proof of it. That's why that has to be neat, and it has to work downward where I can see this is the left side, this is the right side. Let's try number 2. Same deal. The left side is messy. The right side's pretty simple. Let's see if you can't get the left side to end up all simplifying to secant theta. I'm going to begin by changing, I think, this tangent maybe into a cosine over, or I'm sorry, a sine over a cosine. Let's see what that would gain for us. It's not as ideal as I'd hoped because my sines are not going to cancel. Let's see what we can do here. I guess I'm going to go ahead and I'm just going to call it sine squared theta over cosine theta plus, now I could write it as a cosine theta over 1, but I know that I'm ultimately going to have to get a common denominator and add these two fractions together. The common denominator would be cosine theta. So if I take this 1 times a cosine theta and take the top times a cosine theta, it's going to end up cosine squared theta. And then if I combine that together into one big fraction, you should notice the Pythagorean identity that's jumping out at you there. At the numerator, it's just going to be a 1 over cosine theta. And I have a couple options here. Remember that the answer isn't really this final statement. The answer is proving that both sides are the same. And since I'm running out of room here, and I know that I would like to turn that into a secant theta, it doesn't have to. Couldn't I also take this and turn it into 1 over cosine? Either way, if you had gone on and called them both secant theta, that's fine too. You just have to get down to the point where both sides are identical. All right, number 3. This looks a little messier. I've got 2 quantities being multiplied, and somehow it's supposed to equal this. Again, I'm going to work with the messy side first. Probably going to have to do FOIL. Oh, no, I'm not. Never mind. This right here is a Pythagorean identity. I was thinking just go do FOIL, and I think it would have worked. It would have been fine if you chose to do that. You would have still gotten there. But this is a Pythagorean identity. I could get rid of that and just call it secant squared x. And cosine squared x minus 1 is a rearranged Pythagorean identity, but you have to be careful with that. Recall that the Pythagorean identity is sine squared theta plus cosine squared theta equals 1. If I'm going to write this as a cosine squared minus 1, that means that's a cosine squared, and I'd have to subtract the 1. Well, that would mean I'd have to subtract the sine squared back over to that side. And it would look like this. I'd be subtracting, oops, that's not what I meant to do. Sorry. Subtract sine squared theta and subtract the 1 and swap them. Then I'm going to have a cosine squared theta minus 1 equals a negative sine squared theta. Now, you didn't need to really show all of that work. I'm just showing you how this is a rearranged Pythagorean identity, and sometimes it ends up being the wrong sign. So let me kind of box that and get that out of our way. This is going to be negative sine squared theta. It's supposed to equal a negative tangent squared x. I'm sorry, that was supposed to be an x there, not a theta. Now, secant, I'm going to turn it into 1 over cosine squared x times a negative sine squared x over 1. And when you see it like that, hopefully you can recognize that when I multiply my two fractions together, it's going to look like this, which happens to be negative tangent squared x. So I think I'm there. Negative tangent squared x equals negative tangent squared x. All right, how about this one? Pretty messy looking. Again, I'm going to work on the left side. I've got two fractions. These are not Pythagorean identities because they're not squared. So it's tempting to try to call that a Pythagorean identity because it's with the 1, but it's not. Instead, it's a fraction being added to another fraction, and the only way we can do that is if we have a common denominator. We did one similar to this in our homework, probably on the very first day. We're going to take this times 1 plus. On the right side, I'm going to have to take it times a 1 minus sine alpha. And I'm leaving the right side alone. Okay, I'm showing all this work here. Basically, what's going to end up happening is I'm going to have a common denominator of 1 plus sine theta, 1 minus sine theta. I usually just go ahead and merge that. Once I get to the point, that's alpha, not theta. Once I get the common denominator, I'm just going to go ahead and combine that fraction into one big fraction. In my numerator, I'm going to take the 1 plus sine alpha times the 1, that doesn't do anything, plus the other side is going to be a 1 minus sine alpha. And the right side I'm leaving alone. I have some like terms up here. This sine x and this sine x are going to cancel. That works nicely. I'm going to end up with a numerator of 2 from adding the 1's. I'm going to go ahead and FOIL this together, mostly because I recognize that these are conjugates. They're identical except one's a plus and one's a minus, and conjugates always multiply together nicely. Let me show you how. If you multiply the first, we're doing FOIL here, you'd have a 1. If you did outer, you'd have a negative sine alpha, and inner is positive sine alpha. Those two would cancel out. That will always happen when you multiply conjugates. The outer and inner drop out. Last, I have a sine alpha times a negative sine alpha. That will be a negative sine squared alpha. Now I say that they always multiply nicely because the outer and inner drop. They also happen to leave us with a Pythagorean identity many times. 1 minus sine squared alpha is really 2 over cosine squared alpha. And since I'm out of room again, I'm going to go ahead and instead of calling that a secant, I'm going to bump the secant down and call it a cosine. But you maybe have more room and can just go ahead and call them both secants. As we have worked in the past, we've always tried to simplify this down to the most simplest method, and we tried not to leave it as a fraction. But I'm looking at this. This is what I want to see. This can vary from student to student. All right, let's try one more. This one, I'm not sure which side is nicer. I've got the tangent x plus cotangent, and over here I've got the secant and the cosecant. I don't know. I think they're both sides are kind of ugly. What I'm probably going to need to do is turn everything into sines and cosines so I can work with them a little bit better. And can compare the two sides because that's going to be the connection. I'm going to call this sine x over cosine x. Oh, you know what? I forgot to mention this. You're going to find that there are numerous ways to verify these identities. I'm picking the way that comes to me. You might pick a different way and still end up verifying the identity. That is absolutely fine. In fact, most of the time, there's multiple ways to verify it. I will accept any method as long as you're verifying each step solidly that I can see what you're doing and follow it along, and somehow at the end you end up with the same thing on both sides. I don't care which method you use. What you'll find probably is that you'll do it some roundabout way and you check with your neighbor and it took them like one step to do the problem. That happens to me. that's okay. Just makes you smarter. Now that I have all these fractions in here, and at least everything's in terms of sines and cosines, I'm going to go ahead, and on this side, since we're adding, we have to have a common denominator. To multiply, we just multiply straight across. The right side, there's not much I can do. I'm just going to have 1 over cosine x sine x. The left side, I'm going to have to get that common denominator. This fraction needs to be multiplied by sine x. This fraction times cosine x. I end up with a sine squared x plus a cosine squared x all over that common denominator, cosine x sine x. Do you see it? I'm hoping you do. The numerator is a Pythagorean identity. Just going to simplify to a 1. It's nice when you start to see kind of the evolution of that identity, and you start to see where it's headed, and you know, oh, then that'll happen, and those will cancel, and boom, I'm going to have it. It's kind of cool when you start to see those next steps. All right, last type of problem. This is a little bit different. This goes back to what we had done in the previous chapter with solving, and we've done a little bit of solving of trig equations. It says find all the values of x in the interval from 0 to 2 pi for these particular equations. So it's kind of review. I'm not verifying on this. I'm trying to solve it. So let's see what we could do on number 6. When I look at this problem, I look at this like it's a squared term minus a linear term equals my number. I've got a trinomial basically happening. I need to get this set equal to 0 and factor. To factor this, you have to think of that sine squared x almost like it's just an x squared. So you're going to split it sine x, sine x. And then for your last, you're going to find factors of 3. That's just 3 and 1. It's the only thing it can be. But it is a negative 3, so I'll need to make one of those negative and one positive. It would appear that because this is a negative, I'll want my 3 to be negative. Set it equal to 0. Once we factor, we set each of them equal to 0. Solve. And now I'm going to look for values of x. Remember, x is going to be an angle, such that the sine of that angle would be negative 1. Where does that happen? Where is the sine negative 1? Hopefully you're saying, oh, that would happen at 3 pi over 2. That's the only place. But I do have this other half of this equation over here. I got sine x equals 3. I'm looking for the angle whose sine value would equal 3. What angle would that be? Hopefully you're saying, sine only goes to 1. That's the biggest it ever gets. Sine's never going to equal 3. We just have this one answer. Last problem. Let's try a tangent. This one also has a squared term, but there's not a linear term before the constant. I don't think I'm going to be factoring on this. I only have one variable in the whole thing. Let's just start isolating it. Let's move stuff to the other side. Let's add that 2 to the other side. And then I also have this term squared. I would want that gone. I'm going to square root both sides. Remember that when you square root both sides, it's going to be a plus or minus root 2. Every once in a while, we get these problems that aren't off of the unit circle. I know it sounds crazy, but everything doesn't fall on the unit circle. Sometimes you're going to get some other numbers. When is tangent root 2? Well, never on the unit circle. But I could still go to my calculator and get an approximation for that. Let's think through this just a minute before I do it. If you think on your unit circle, I know that tangent is root 3 up here and here. Root 3 is a little bit bigger than root 2. Tangent's probably going to be just a hair below that, a little bit smaller than pi over 3, a little bit smaller than 2 pi over 3, or actually it'd end up bigger as you're wrapping around, sorry. Let's see if we can figure that out on our calculator. I'm just going to type in my calculator, and this is going to take a little bit of work. I'm going to do inverse tangent of root 2. I get 0.955. I'm just going to call it 0.96. That is the first radian measurement that would have a tangent of root 2. The problem is that this 0.96 that I have would happen multiple times. It would not always at 0.96, but just like I showed you, it would happen here. It would also happen here. You would also have it happen down there, and you'd have it happen down there. You have 4 places where that can be a positive or negative root 2. Right now I found the first one. If it helps you to think about this, we need to leave it in radians because the domain was in radians. But if you think of that in a unit circle format, remember that going clear over here is pi, or about 3-ish, which means right here is about 1.5-ish. 0.96 is somewhere where I drew that black line. I would also have that right here. What I'm going to do on my little diagram is I'm going to show you that this right here, this measurement, is a 0.96 radians. And we're going to use that 0.96 to find these other black marked angles. I need to find, it's going to start getting cluttery, I need to find the angle that goes clear over to here. Well, the unit circle is very symmetrical. This here would have to be a 0.96 also. And this down here would be a 0.96, except that it happened to be negative. This down here would happen to be a 0.96. All of those would be symmetrical. Let's come up with all the different angles, though, as you wrap around the unit circle. I've got my 0.96. To get this angle right here that I've marked, probably the easiest way to find that would be to take pi, subtract out the 0.96, and I'm right here. I'm going to take pi in my calculator minus 0.96. The next angle measurement would be a 2.18. To find this marked angle, I would take pi and add the 0.96. This makes you appreciate the unit circle when you have to start dealing with all these funny things. The last one would be this one here, and the simplest way probably for me to get that would be to take 2 pi, subtract the 0.96. We actually have 4 answers, not on the unit circle. Now you start to appreciate when they do fall on the unit circle, so you just know them versus having to go figure them all out. But once you do know one of them, like once you find that initial one, because it's all symmetrical, you should be able to fill in that angle in different places to find anything else. All right, hope this helps. Go have fun.